The AI-related technique used by our group in this assignment is reinforced learning. One of the points I found interesting was the choice of a discount factor gamma value and learning rate alpha. Gamma, which is 0.95 in its implementation, serves as a discount factor that determines the relative importance of future reward compared to immediate reward in the agent's decision-making process. A mathematical formula where gamma appears most prominently is in the temporal difference error calculation. So as we can see from this formula, in this equation, gamma multiply the maximum Q value achieved in the next state, effectively reduce the weight of a future reward by 5% compared to immediate reward. It's still 0.895 value represents a balance between short-term and long-term thinking. It is high enough that the agent still cares significantly about future consequences of its actions, but low enough that immediate rewards carry slightly more weight. A choice of 0.95 is based on empirical research in reinforcement learning, showing that the value between 0.9 and 0.99 typically work well for strategic games where both immediate and future consequences matter. And alpha set to 0.01 functions as the learning rate that control how quickly the agent updates its knowledge based on new experiences. This parameter appears in the y update formula. So in here, where it scales the magnitude of y adjustment. The relatively small value of 0.01 means that each individual experience causes only a 1% adjustment to the y selected by the TD error and the eligibility traces. This conservative learning rate is deliberately chosen to ensure stable learning. If alpha were too large, the agent's policy would first fluctuate widely as it encounters new experiences, potentially causing it to forget previously learning strategies. Conversely, if alpha were too small, the agents would learn extremely slowly and might not adapt quickly enough to changing game situations.
One of the most interesting parts of our agent is that it doesn't always pick the move with the highest score. That's because we use MCTS and inside it, a strategy called UCT, which stands for Upper Confidence Bonus for trees. UCT balances two things: the average value of a move, how well it's performed so far, and the exploration bonus, which encouraging trying less validated options. Now, in most textbook samples, the formula is average value plus A times the square root of log of the parent visits over self visits. But in our agent, we simplify it to the average value plus A times the square root of 2 times parent visits over self visits. We choose this version for two reasons. First, it's faster. We avoid computing the logarithm. Second, it gives a slight stronger push to explore early on when the tree is still shallow. We also use the C equal to 1.4, which is a commonly accepted value that balances exploration and exploitation. Too small makes the agent greedy, and too large makes it unstable. In our one test, our agent skips a strong center move and instead uses one eject block the opponent. That choice didn't look smart at first, but 2 turns later, it led to a win. That's not luck, it's the UCT helps the agent look beyond the obvious. So to us, UCT isn't just a formula, it's the reason our agent behaves with curiosity and adapts to certainty and keeps learning as it searches.
MCTS is basically a loop of 4 steps, and today I will introduce the simulation part of the MCTS for my agent. And the simulation part first, for me, I will we will expand the new node in our search tree, and before that we will copy the current board and run up the fixed number of turns. And first off, we will scan for any move that gave us an instant win. If we find one, we will do it right away. If not, we will use the epsilon greedy style. We just set a very small value for epsilon. Why we use this strategy? Because that will increase our diversity, and it also prevent us trapping local, and that's the reason why we should take the random choice. After that, we if we don't pick the random random move, we will go to the next one, which is the greedy strategy. Greedy strategy picks try to knock out the opponent and stretch with the strong card jack, and after that we will grab center squares if we can, and after that we will choose the spot that, you know, using our placement heuristic, like which is the best move, and after that we will simulate all the turns, and we have the best score, best move, and that will help the tree to guide our next real move. And that's it.